Hello everyone, I'm Norman Wildberger. We're setting out a new foundation for arithmetic and algebra, in fact mathematics more generally, here based on multisets and thinking about numbers and polynomials and consequent algebra, all built in terms of these multisets. And a key sort of novelty in this approach is that we end up having to adopt some of the 20th century physicists' ideas having to do with particle-antiparticle duality to create a theory of negative numbers. So we've done that. Now we're in a position to reap some of the very important consequences. So I'm aspiring here not just to create a new foundation for the subject, but also to position us in a way that we can see things in a new light. And you're going to see that happening very strongly today. We're going to be looking at polynomials with a new point of view that will open up all kinds of interesting developments. And in fact, it will turn out that we will end up being able to reinterpret some very important 20th century physics developments in terms of this very elementary algebra. So we're heading in that direction. Okay, so we're going to be talking about integral polynumbers. So let me remind you that a polynumber itself is an M set of natural numbers. For example, here, there's an M set of natural numbers interpreted as 2 plus alpha plus 3 alpha to the 4. And here's our usual convention in the algebraic calculus course, for example, for expressing such a polynumber. Now, somewhat novel, an integral polynumber is an M set of integers. Integers now. So that includes not just natural numbers like this, but also negative numbers. And I like to often express negative numbers with the natural numbers with a bar over them. So this is -3, that's -3, that's -1, etc. Now this corresponds on the polynomial side, in terms of powers of alpha, to the following. This is really there's two of these alpha to the -3, or 3 bar. There is a single alpha to the 1 bar, or alpha to the -1. There's a 1, and then there's 3 alpha. And perhaps more usually, okay, if we sort of adopt the usual convention for negative signs, it's a more familiar way, it'd be 2 alpha to the -3 plus alpha to the -1 plus 1 plus 3 alpha. So in algebra, this is not a polynomial because there's negative powers of the variable appearing, sometimes called a Laurent polynomial, or sometimes a rational function. Okay. In any case, we are going to augment this notation. Okay, we're going to make it a little bit bigger to allow us to incorporate also coefficients of negative powers of alpha in sort of an obvious way. But we're going to have a little bit of an addition now. So the 1 plus 3 alpha will be represented by the 1 here and the 3. So this would be the usual polynumber story. Okay. What I'm now going to do is going to include the coefficients of alpha to the -1, alpha to the -2, alpha to the -3 up above here. And now there's a sort of a symmetry here, which will become very important in this lecture. Okay. There's a symmetry here where this central object, which is the coefficient of just the constant term, sort of plays a central role now. Okay, the strictly positive, the strictly negative ones on either side of it. And so to make that clear, I'm going to put a double bar there. Okay, so those 2 bars there are going to frame the constant term, or the alpha to the 0 coefficient. All right, so that's what an integral polynumber is. And we're going to be seeing some interesting things about these things today. Now, we particularly like doing arithmetic in the domain of integers. So we're also going to allow ourselves to consider integers as coefficients of our powers of alpha. And that manifests itself in having anti-integers inside our M set, defining the polynumber or the integral polynumber. So have a look at this thing here. This is an ordinary polynumber, okay, with natural number entries here, but some of them have antis. So there's a 0 ante, 0 ante, 1, 1, 1, 3 ante. And these 2 0 antis are representing the number -2. So we just had M set 0 ante, 0 ante, or anti-0, anti-0. That would be the number -2, or 2 bar. There's still 3 alphas here represented by these 3 1s, and there's a single alpha cubed but there's an ante here, so we have to take minus that. So in conventional notation with the more usual conventions, this would be minus 2 plus 3 alpha minus alpha cubed. Okay, so that's a Pauli number. But now we can combine these two different roles of integers here, okay, and consider integral Pauli numbers also with integer coefficients, okay? So that means that we have, inside here we have integers, so not just natural numbers, but also negative numbers like -1 and -2, etc. But we also have antes, okay? So this is 2 bar ante, 1 bar ante, 1 bar ante. It corresponds to, this 2 bar, okay, corresponds to alpha to the -2 or alpha to the 2 bar. But the ante means that there's -1 of them, okay? So there's a -1 or minus alpha to the -2 represented by that thing there. There's 2 of these 1 bar antes. So the 1 bar is telling us that we're talking about alpha to the -1. And the antes representing the fact that we don't have 2 of them, we have -2 of them. So -2 alpha to the -1, or in more legally, plus 2 bar alpha 1 bar. And then there's a 0, that represents 1, and these 3 2's give us 3 alpha squared. Okay. So if we want the usual notation for negative numbers, we could also rewrite the M set. Instead of having 2 bar, we could write -2. Okay, so instead of the 1 bar, we could write -1, etc. So it amounts to the same thing. But there's a lot of negatives here, and there is definitely the possibility of confusion here with this minus sign. The minus sign being here, even though it's very familiar, right? It's in the place where an operation usually is. So there's an operation sign there, and it looks like there's an operation sign here, but you have to sort of interpret that operation sign is not really an operation sign, it's rather negating the two. So this is not really optimal notation. So I want to move you a little bit towards something more in this direction where the operations and the negations are more clearly delineated. Now, when we're doing calculus or analysis, there is a big difference between the world of polynomials and the world of rational functions, what we're calling the difference between polynumbers and integral polynumbers. So that's what you get when you view all of these things as functions. So in 20th century mathematics, the idea of a function was all pervasive, okay? A lot of things were attempted to be framed in terms of functions. A rule that assigns something of a certain kind as input and then gives you an output of some other potentially different kind. So in my view, this sort of active role of functions is overplayed. Okay, it's a too frequent concept in modern mathematics, and it leads to a lot of confusions because this dynamic aspect, okay, of taking an input and doing something to get an output necessarily really involves a deep dive into computational issues, to issues of programming, issues of computation, issues then correspondingly of memory and language, etc. So I'm going to strongly advocate to you that you should not think about polynomials or polynumbers or integral polynumbers as functions primarily. And if you're an undergraduate, if you've done a mathematics degree, this will be sort of so ingrained into your thinking that it will be a bit of a challenge to move back from that, but it has a lot of benefits, okay? So the usual story, let's look at it with the distinction between these two examples. So here is a Pauli number on this side, and here's an integral Pauli number. This one is 0, 1, ante 3, 3, corresponding to the polynomial 1 minus alpha plus 2 alpha cubed in the usual notation. And here, there's a kind of a negation of this in some sense. So we're sort of replacing each of the numbers here with their negatives. So we have a 3 bar, a 1 bar ante, and a 0. And that corresponds to the integral Pauli number 2 times alpha to the -3 minus alpha to the -1 plus 1. Now, in a calculus course, or an analysis course, you would look at these things in terms of functions. You would say, aha, this thing here really represents a function, say y equals p of x, given by this polynomial. Okay? So you input x and you output y. And correspondingly, this thing here is also a function, 2 over x cubed minus 1 over x plus 1. You input x, you output y. But in the world of functions, these things are hugely different. For one obvious reason is because as a function, this thing here with the x's in the denominator requires you to avoid an input of 0. Okay? So because what you put in 0 here, it doesn't give you anything that's defined. So the domain of this thing is automatically different from the domain of this. But also visually, in terms of a graph, they're very different kinds of objects. There's a graph part of this thing here, sort of a familiar cubic kind of shape. And here is perhaps a less kind of familiar, somewhat hyperbolic, but it's not exactly, sort of shape with this singularity at x equals 0 represented by these two branches that go up and down here. So a manifestation of the huge difference between these two things is when we come to the fundamental question of integration in calculus. Now, if you say integrate this thing from, say, 1 to 2 over this interval here, the area of that turns out to be exactly 7. Okay, that's an exact calculation. While over here, the corresponding integral from 1 to 2 of this function, okay, turns out, if I ask my computer, it's 7 over 4 minus log 2. Okay, it's a standard integral that high school students or undergraduates learn to do. Now, we say this answer here rather glibly, okay, but really this answer is hugely computationally problematic, because this log 2 here represents a process which doesn't actually terminate. So you can't actually compute it. So the question about whether there is an it that we're legitimately talking about here is highly questionable. If you ask the computer, well, it'll just spew out some number of digits, okay? But it's clear that you're not able to really obtain this thing exactly. So it's important to state, as I've done in many places, that this thing over here is intrinsically an approximate calculation, okay? While this one over here is exact. So there is a world of difference between these two computations. This is really applied mathematics, and over here this is pure mathematics. And moreover, in the algebraic calculus course, okay, we learn that we can do this kind of integral without any of the infinite machinery that's used in classical calculus or analysis courses, in terms of Riemann integration, in terms of setting up Riemann sums and subdividing things and having rectangles and upper and lower bounds, etc., and then taking some limit as the net or the size of the rectangles goes to 0. Okay? We can completely avoid that and stay completely in a purely polynomial, purely finite sort of calculating algebraic situation. Okay? So that's a big departure from the usual calculus story. Okay? Found in the algebraic calculus course. Lectures are over in the Wild Egg Mathematics channel. So this really is an exact theory. Okay, we do not need Riemann integration or Lebesgue integration. Absolutely not, right? We can address this kind of integral in a completely algebraic way. But this thing here is necessarily approximate. So you can see that from the calculus point of view, there is, in fact, yes, a huge difference between this object and this object, especially when we view them as functions. But I'm going to ask you here, because we're doing arithmetic, we're doing algebra, to step back from this calculus orientation. Calculus over there. We're going to look in this direction rather at algebra, okay? And when we are just looking at the algebraic side, the distinction between these two things is much less obvious. In fact, they're actually very close to being sort of symmetrical. Okay, so we're taking an algebraic approach. We're letting go of the function concept. How then are we to interpret what the meaning of these polynumbers are, whether they're polynumbers or integral polynumbers? So let me give you an alternate way of thinking about what these things are, or at least how to interpret them in a kind of a visual or a physical fashion. Actually, the question of what the are is already contained in the definition. They are just multisets of natural numbers or multisets of integers. That's what they actually are, okay? But now the question is, how do we think about them? So here is what I'm proposing, that we're going to think about these things as densities or measures. It's like we have a number line, okay, and it's actually sort of a discrete number line for us currently. So imagine the natural numbers sort of strung out on a line here. There's 0, there's 1, we've marked these things, there's 2, 3, etc. We're going to think about a polynumber like this one, 2 minus alpha plus 3 alpha to the 4, as being a bunch of weights which are positioned over these various natural number positions. The weights can be bigger or they can be smaller. They can also be negative, corresponding to sort of like, an upward force instead of a downward force. Okay? It's like a density or a measure. Okay, so this thing here, 2 minus alpha plus 3 alpha to the 4, is going to be represented physically or visually by this mass distribution. Okay, so the way you should think about this, here's the number line, and you see here there's a kind of a stack of two things. So think of this as like a unit weight of some kind, a little metal bar perhaps, okay? So there's two of them stacked up on top of 0. That's corresponding to that 2. Down here, there's sort of one in the negative direction, sort of corresponding to a negative force. Okay, so it's down in that direction. That's corresponding to the minus alpha. And over here, there's 3 of them over the 4. That's corresponding to 3 alpha to the 4. Okay, so having done that, the transition to an integral Pauli number, or an I-Pauli, is not hard. We're just going to extend this story where now the base number line goes in 2 directions. So now 0 is in the middle there somewhere, and 1 is over here, and 2 is there, and over on this side, minus 1, minus 2, etc. So it extends in this direction as well as this direction. So now we have more room to put weights, positive or negative. That's all what we're doing. We're just extending the number line from sort of a one-sided, discrete framework to a two-sided, discrete framework. Okay, so this thing here, alpha to the minus 3 alpha to the minus 2 plus 4 plus alpha squared, there it's represented. So there's alpha to the minus 3 represented by this point here, minus 3 on our number line, and there's a weight of 1 because there's one of these. And then over minus 2 or under minus 2, there's a weight of 3 because it's minus 3 alpha to the minus 2. Over 0, there's 4, that's representing that thing, and over the 2, there's just a single 1, representing the alpha squared. So this is visualized as a density or measure on the positive number line, essentially a discrete number line indexed by natural numbers, while this one over here is visualized as a density or measure on the entire two-sided number line, which is again discrete and labeled by integers. So in this sort of continuum here, or this sort of step-by-step, there's also more elaborate algebraic objects, also built from Pauli numbers in a natural way, called rational functions, which are just quotients of Pauli numbers. So that is a bigger theory. In some sense, you can, of course, think about these things as being sort of special cases of this. But we should just be aware that further on down the road, we do ultimately want to talk about these things as well. From the calculus point of view, these things are even much more complicated and sophisticated than the problems that we get with the I-Pauli and the 1 over x. The complexity is massively bigger here, okay? Oh, that's not properly understood in most calculus courses. Okay, but we're sticking here to this framework here. So now we have a somewhat balanced point of view on how to think about what Pauli numbers are, how to think about what integral Pauli numbers are. And they're pretty well the same kinds of things, just over different domains. So let me explain how you should think about the arithmetic of these integral Pauli numbers with this sort of density or measure point of view. The addition is pretty easy. So here's an example. P is alpha to the minus 2 plus 1 plus 2 alpha. Alpha to the minus 2, that weight, the 1 over the 0, and the 2 stacked on top of the 1 representing 2 alpha. Over here is another one, minus 2 alpha to the minus 1, so weight of minus 2 at minus 1, and a weight of 1 at 1. So if we add these things, what we do is we just add the two densities. We just combine them in the obvious way. So if we combine these two things, there's the number line, so that density is coming from there, that one's coming from there, and two of these are coming from there. And then when we add this one, well, we have to put this 2 down here under the -1, and we have to put another 1 on top of the 1. So we get this picture here, which corresponds to the polynumber alpha to the -2, -2 alpha to the -1, plus 1 plus 3 alpha. Now, the multiplication, however, is more complicated and more interesting, and corresponds to what's called in measure theory convolution. So this convolution of these two measures. So let me try to illustrate what's going on here. Here's the result that we get just by doing the algebraic product. So the way we do it visually is we say, okay, what we're going to do is we're going to take this thing here, think of this thing as a fixed mass distribution, okay, which is sort of centered at 0, okay, so it's centered at 0, fixed mass distribution. And we're going to put various copies down of it in various positions to make a cumulative mass distribution. And the places where those copies go and the sort of sizes of the contributions are determined by this one. Okay, so let me illustrate that here. So over here there's a 1 at -2. That's at -2. Okay, so what I'm going to do is over here I'm going to move over so that I'm sort of centered at -2 temporarily, and I'm going to put a copy of this thing, which is currently centered at 0. Just imagine copying it down here. Okay, so I'm not going to write the bars. I'm just going to go like this. Okay, that's representing that -2 there. That's sort of 1 over from where we're centered here, so we've put that one there, and there's also a 1 going up, 1 to the right, okay, so 1 up there, okay? So this mass distribution here is just a copy of this one, but it's suitably translated so that it's centered at -2, okay. And over here, now the next one is this 0, okay? So this thing here has a weight of 0. That means we have to take a copy of one of these, because it has a weight of 0, and translate it so that it's centered at 0. Well, that's exactly where it is already, okay? So that means we have to take this thing, basically just copy it down here. So what does that mean? Well, under -1, we have 2. Okay, I'll do it like that, okay? And over 1, we have a 1. Right? So we've copied this thing so it's centered at 0. And now, in addition, we have to take this thing here and we have to copy it so that it's centered at 1. But now we have to also double that mass distribution because there's a factor or weight of 2 here. So really we have to take 2 times this thing and position it so that it's centered at 1. Okay, so let's do that, okay? So I'm going to take this thing here and I'm going to center it at 1, but I'm also going to multiply it by 2. So this thing here, which is a weight sort of -2, is going to come down from here to weight -2, but then it's also going to keep going because I have to multiply it by 2. So there's really a weight of 4 there. Okay, and then that's centered at 1. Then on the right of that, at 2, we have to also put one of these, but I also have to double it. So not just 1, I have to go up like this. So that's how we convolve things. We take a copy of this thing and basically make copies of it in various places determined by the positions and the weights determined by this other one. So let me just see if we get the same thing that we did algebraically. So here there's a -2 alpha to the -3, yeah. What about alpha to the -1? Well, you see here there's some cancellation because there's sort of a positive weight and there's also a -2 weight. So the total weight is -1 at -1. So there's a minus alpha to -1. Here there's a weight of -4, here there's a weight of +1, and here there's a weight of 2 at alpha squared. So that's the same thing that we would get. Now you can convince yourself that this is the same thing that we would get if we interchanged the roles of these two things. In other words, if we took this thing and made copies of it according to the weights and positions of these guys over here. So I'll let you check that we're going to get the same thing. Okay, so this is showing you that in this interpretation of having densities or measures, okay, the addition corresponds to just a sort of a cumulative addition of these measures in the simplest possible way. While the multiplication is also attractive, but it corresponds to this important operation called convolution, which is important in engineering and analysis and many things, okay? So it arises in many places, but this is sort of an elementary way that it arises when we have this interpretation of these integral polynumbers as densities or measures on this discrete number line labeled by integers. Okay, now I want to suggest to you that this way of thinking that I'm giving you here actually has a really great consequence just a little bit further down the road when we are in possession of rational numbers. So currently we've got natural numbers and integers. Okay, we don't have rational numbers yet, but that will not be a big ask because we all sort of know how to go from integers to rational numbers in some fashion or another in terms of, you know, formal quotients or ordered pairs or something like that. So that's not going to be too much work. But once we do have rational numbers as part of our number system here, then we're going to be able to adopt this point of view exactly that I'm expressing here in this video to really expand our minds about the objects that we think of in analysis in one way. We're going to be able to think about them in a very different way from an algebraic point of view. So once we extend our number system to the rational numbers, then we can make the following definition, that a rational polynumber is then an M set of rational numbers. Okay, that's kind of obvious thing. So for example, here then is an M set of rational numbers. So here's the rational number 2/3, 15 over 7, 0. Okay, and these bars over here are just negative. So this is negative 2/3, negative 2/3, and this ante is the usual ante. That's an anti-zero. So in terms of a polynumber or a rational polynumber, there's two of these minus 2/3. So that would correspond. We would write that down in alpha notation as 2 times alpha to the minus 2/3, because there's 2/3 appearing here. Actually, minus 2/3 appearing here, so we get alpha to the minus 2/3, two of them. There's a minus 1 because there's an anti-zero. And this 15 over 7 would correspond to alpha to the 15 over 7. So think about this for a second. We are creating these things as legitimate mathematical objects without a prior theory of cubed roots or seventh roots. Right? If you go into a first-year calculus course and you say, what do we mean by the function y equals x to the 15 over 7? Well, that's not going to be so easy for them to explain. They'll try to tell you that, well, this was a function that involves raising something to the 15th power and also taking a 1/7 root. And then you ask them, well, how do you take a 1/7 root? And they go, I don't know, you use a calculator. Okay, so that's the way they think about it. They think this is something that inputs a number, and then you have to use a calculator involving this rather complicated 7th root operation in order to calculate the result. What we're doing here is invoking this as a legitimate mathematical object without any mention of 7th roots or cubed roots or anything else. It's just a multi-set of rational numbers. And it can be represented physically in a very parallel way to what I've already explained. Okay? It's just that now our number line is to be thought of as being sort of expanded, not just discrete in terms of the natural numbers or the integers. We're also considering rational number positions. Rational numbers, completely obtainable in a finite amount of way, no infinite processes or dreaming required. So this thing here, well, we just find the point minus 2/3 on our number line, somewhere between 0 and minus 1. And over that point, well, there's two of these. So we put a weight of 2 over minus 2/3. And here's 0. Yes, here's 0. There's minus 1 of them, so we put a weight of minus 1 at 0. And over here, 15 over 7, it's a little bit more than 2. Okay, there's that point. Over that point, we put a weight of 1. So there it is. There's no irrationalities involved here at all. There's no irrationalities in sight whatsoever. That is such an important point to make. Okay, we are doing something different from what you find in undergraduate courses. We're looking at things in a different point of view. It's all just M sets. Okay, now with this framework, we're in a position to introduce something really exciting, which is a fundamental symmetry in this situation. Here's our number line, there's 0, natural numbers over here, 1, 2, 3, negative numbers over here, -1, -2, -3. There's a symmetry here. We can look this way, we can look this way. They look pretty well the same in both directions, just this is going to the right and this is going to the left for you. There's a symmetry, that reflection symmetry about this central point. If you've been watching my Maths and Music series, I talk about symmetry in the piano and the difference between translation symmetry and reflection symmetry. It's an important topic. And so this is an example of where the reflection symmetry about 0 plays an important role. So typically speaking, if we have thinking of a number line as giving us a positional information. We have some physical structure and we want to, allocate positions to various things. Maybe it's a road and these are street numbers, or it's an industrial assembly line and here's the various markers on the assembly line. When we have that kind of thing, the translation invariance is almost always more important than the symmetry. But in this situation here, we're looking at the number line as a representation of this arithmetical structure. Okay, it's not just positions we're talking about. We're talking about having arithmetic here. And in arithmetic, 0 does play a very distinguished role. 0 is very special. It's like the most important point on the number line. So the symmetry about 0 naturally plays a role in arithmetic. As opposed to the piano, you're not doing arithmetic on the keys, you're just going up and down. It's the translation invariance that's important. Okay, so what we're going to do now is to look carefully at this fundamental symmetry that's appearing here, which is largely invisible to undergraduates, okay? Because from an undergraduate point of view, as we've talked about already, there's a big difference between the function f of x equals x and the function f of x equals 1 over x. There's not a lot of similarity between those two things. They're very different. They look different, their graphs are different, their integration theories are different, their arc length formulas are completely different, etc. So, but we're moving away from the calculus point of view and just looking at this algebraic side of things, and there the symmetry is really important. So, an example. So here is an integral polynumber. Weight of 1 at -1, weight of -1 at 1, a weight of 3 at 2. So it's alpha -1 minus alpha plus 3 alpha squared. And here is this reflection symmetry. Well, let's call it sigma, okay? Sigma. And what does this do? Well, it just reflects everything around 0, okay? So that tower goes over there, and this little underneath thing goes over on this side, and this thing here goes on the other side. And algebraically, what we do is we just negate all the exponents, okay? So we're getting 3 alpha to the -2 minus alpha to the -1 plus alpha. More generally, sigma of alpha to the n equals alpha to the -n. And otherwise, we're sort of using linearity to extend that to more general polynumbers or I-polynumbers. Now this symmetry operation on integral polynumbers satisfies a number of pleasant properties. The first one is that it's an involution, that if you do it twice, you get back to where you started. You reflect, and you reflect again, you're back to where you are. So sigma of p equals p. It's linear. Sigma of p plus q equals sigma of p plus sigma of q. It's also linear in the sense that if k is an integer, okay, you multiply a polynumber by 2 and then reflect, well, you're going to get twice the reflection of the original. And this one here, a little bit more subtle, that the sigma of a product is the product of the sigmas. Okay, sigma of pq equals sigma of p times sigma of q. So this is a pretty natural algebraic symmetry, which is in some sense at the heart of algebra when we look at integral polynumbers in this fashion. So for our last slide, we're going to introduce symmetric and alternating integral polynumbers. We'll say that a polynumber, an integral polynumber, is symmetric precisely when sigma of p equals p. That means that when you look at it, it's symmetric. Everything to the right looks very much like everything to the left. symmetrically. So for example, this thing here, 2 times alpha to the minus 3 minus 4 alpha to the minus 1 plus 1 minus 4 alpha plus 2 alpha cubed is symmetric. And conversely, P is alternating, or maybe in some other context we could say skew symmetric or anti-symmetric. Okay, but let's use alternating. When sigma of P equals minus P, same as P bar. So for example, this thing here, Q equals 3 alpha to the minus 5 minus alpha to the minus 1 plus alpha minus 3 alpha to the 5. This thing's alternating because when you apply sigma, you're going to get minus 3 alpha to the minus 5 plus alpha inverse minus alpha plus 3 alpha 5. You're going to get exactly the negative of this thing. So having this sigma reflection allows us to identify two sort of interesting classes, two particularly natural classes of integral polynumbers, the symmetric ones and the alternating ones. And in fact, there's sort of a nice way of cooking these up in quite great generality. So if you have any integral polynumber, P, then P plus sigma of P is symmetric, whereas P minus sigma of P is alternating. That's an easy check. So now we're at the door of a kind of an untold chapter of algebra, a missing chapter of algebra that probably you should have learned about in grade 9 or grade 10 when you were learning about polynomials. But at that time, you thought that polynomials were only things that you cooked up with positive powers of x or y or whatever. But now from this larger point of view, positive powers, negative powers, these things are naturally viewed together. When we do that, we come to this new chapter of algebra, which we're going to start investigating next time. And there will be all kinds of interesting consequences with some actually quite sophisticated mathematics and physics. Hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.